Tesla has set its sights on 2026 as the year when the Model 2 finally moves from concept to reality, with mass production as the crucial turning point. The idea is straightforward but ambitious: produce vehicles at a pace that not only lowers the monthly cost of ownership but also maintains consistent quality while reducing the wait time from order to driveway. By scaling production, Tesla plans to deliver tangible benefits to buyers, from fewer bottlenecks in critical stages like paint and wiring to shared modules that accelerate assembly. At the same time, the Model 2 is being engineered with a thermal management system designed to keep the car efficient in both heat and cold, ensuring that owners see daily advantages. In practical terms, this means a workweek's worth of range so drivers are not constantly chasing chargers, faster top-ups on highways, features that anticipate cold weather challenges such as snow and salt, and driver assistance that supports without constant reminders. Even the interface has been designed to be intuitive enough to learn once and use effortlessly thereafter. The essence of this strategy is that mass production does not remain a corporate slogan but becomes the factor that makes the Model 2 accessible, affordable, and reliable for everyday use. What ultimately transforms the Model 2 from a vision into something people can actually buy is Tesla's commitment to scaling production effectively. When a car enters large-scale production, supply stabilizes, trims are available consistently, wait times shrink, and buyers do not have to move to higher-priced versions simply because of shortages. A steady production rhythm ensures that one vehicle leaves the line at fixed intervals, keeping bottlenecks like paint or wiring from stalling progress. At an annual scale of several 100,000 vehicles per plant, shaving even seconds from each production cycle significantly boosts weekly output. As a result, the waiting list shortens, and popular configurations remain available rather than becoming limited editions. Volume is not just about speed but also about cost. Higher output lowers the per-unit cost along the experience curve because equipment, processes, and workforce become increasingly optimized. The battery pack, the single most expensive component, becomes cheaper as scale improves. For example, if the roughly 50 kWh pack falls by another $20 to $30 per kWh compared with early production, total cost drops by $1,000 to $1,500 per car. Spread across a 60-month loan, this translates into noticeably lighter monthly payments. Over time, as Model 2 volume increases, key subsystems such as the motor, inverter, thermal system, and zonal wiring also get refined, so the financial burden continues to decline steadily rather than just once. Quality also improves at scale. When manufacturing processes are repeated at high cadence, assembly variation decreases, and process capability strengthens. Weak spots such as paint finishes, electrical connectors, and thermal lines are standardized through shorter harness runs, reduced connector counts, and modular testing, which means fewer minor problems for new owners and less time in the shop. With steady output, Tesla can forecast regional parts demand more accurately, allowing owners to schedule service appointments with confidence that parts will be in stock, repairs can be finished in a single day, and downtime will be minimized. In short, mass production for the Model 2 provides consistent trims, lowers monthly costs, and ensures a smoother ownership experience, making it not just a product but a viable long-term option for mainstream buyers. The Model 2 has been engineered from the start with mass production in mind, with its low variation structure enabling stable assembly and reducing costs. Technical decisions prioritize not only speed of production but also everyday durability and convenience. The body design, for example, uses one blueprint from multiple trims with shared mounting points and symmetric panels, reducing the number of unique stampings and dies by as much as 20 to 30%. This approach shortens tool changeovers, lowers tooling costs per car, and streamlines inventory. With such foundations, maintaining a cycle time of 60 to 75 seconds per car is achievable, translating to 48 to 60 cars per hour, or nearly 4,000 vehicles per week on a 2-shift, 5-day schedule. This level of consistency transforms the Model 2 into a dependable product rather than a paper promise. To prevent bottlenecks, Tesla is rethinking the paint shop, which traditionally slows production. By reducing decorative layers, relying on durable colors, and applying protective films at the factory, paint time is shortened significantly. The critical clear coat process, which once consumed 20 to 30 minutes, is streamlined, while rework caused by dust or scratches drops from about 3% to near 1%. In a plant producing 5,000 cars weekly, this improvement eliminates around 100 rework jobs, saving hundreds of labor hours and maintaining a consistent production rhythm. Wiring, another typical trouble spot, is also redesigned. Traditional harnesses can extend nearly a kilometer in length and weigh up to 60 kilograms. The Model 2's zonal architecture reduces this by 20 to 30%, saving material weight, eliminating hundreds of connectors, and decreasing potential fault points. Fewer connectors mean fewer early life failures, while automated end-of-line electrical checks by zone make the process quicker and more accurate. Together, these innovations ensure higher first-pass yields and faster, more reliable assembly. Thermal management is another critical area where efficiency directly affects both performance and long-term reliability. The Model 2 employs a unified thermal system that manages the battery, drive unit, and cabin together, reducing the number of valves and joints by nearly 40% compared to split systems. With fewer potential leak points, everyday benefits include faster and more efficient charging sessions, dropping from 30 minutes to roughly 22 to 25 minutes under favorable conditions, as well as better performance retention in cold weather. The battery pack itself is designed with modularity in mind. A standard shell accommodates different capacities, allowing Tesla to swap core cells while maintaining the same outer mechanics. This streamlines assembly and testing while giving customers flexibility between a cost-friendly 48 to 52 kWh version with LFP cells or a longer-range 60 kWh option. The cost difference between packs is around $1,000 to $1,200, giving buyers real choice without complicating the factory line. To maintain efficiency across the range, Tesla standardizes propulsion hardware, motors, inverters, and drive shafts are identical, with performance differences unlocked by software. This approach reduces factory complexity, increases yield, and lowers assembly time while allowing customers to pay later for performance upgrades without needing new hardware. Even seemingly small details such as fasteners, clips, and seals are streamlined, with the variety cut by more than half to reduce tool changes, improve consistency, and prevent long-term squeaks or torque issues. Standardizing parts also makes service faster and easier across Tesla centers, ensuring consistent care for owners no matter their location. All of these production-focused choices are tied to real-world ownership benefits. The Model 2 is designed for easy daily life, beginning with a range that suits an entire workweek without daily charging. Energy efficiency is improved by refining regenerative braking for urban driving speeds, optimizing aerodynamics, and preconditioning the battery pack based on routes so range and performance stay consistent from the first mile. For colder climates, Tesla has engineered protective measures for the underbody in critical areas exposed to snow and salt, while adding practical features like a heated charge port and pre-warming routines to keep charging speed stable even in freezing conditions. With one tap, owners can warm the cabin, clear the windshield, and balance energy use without sacrificing comfort or efficiency. Driver assistance is built to reduce fatigue without overwhelming the user. The system combines radar and cameras for redundancy in challenging conditions such as rain or snow, while software updates are designed to improve reliability without forcing drivers to constantly relearn the interface.